Good afternoon, InfraGard members across the nation. My name is Corey Burke, and I'm the Program Manager of Education and Technology with InfraGard National Members Alliance. I'd like to welcome you to today's presentation, Why Locks Fail, a practical look at insecurity engineering, a special program brought to you by InfraGard National and our friends at Security Laboratories. Security Laboratories is a leading research and consulting group dedicated to advancing the science of physical security by testing, analyzing, and improving mechanical and electronic locking systems around the world. We'd like to extend our sincere thanks to Security Laboratories for their continued partnership and support of our mission. We'll be taking questions at the end of this presentation, so please enter your questions in the question box at any time. This webinar is open to the public, and you'll receive the full recording in your follow-up email later on next week, along with your CPE certificate. Joining us today is Marc Tobias, founder and lead investigator at Security Laboratories, and author of the 2024 publication, Tobias on Locks and Insecurity Engineering. Marc will take us behind the scenes of modern lock design to explore how and why locks fail, and what lessons we can apply to build more secure systems. Marc, welcome, and thank you for joining us today. Take it away.
Hey, thanks a lot, Corey. So this webinar is to give you an introduction to basically what we do in analyzing essentially mechanical but some electronic locking systems and access control systems, and how we find vulnerabilities. The book on the screen I wrote last year by Wiley, and it's a very detailed treatise, 700 pages on all aspects of insecurity engineering. So I'll go through the first part of this webinar. I'll go through a slide presentation, some of our rules that we use in lock design, and then the majority of this presentation will be video of different cases that we have worked from simple to complex. Some you may be familiar with, probably a lot you are not. Some of these involve very high security locks. Some are pretty simple. And like I said, some case examples you may be familiar with. So I'll go through this. Just as a brief background, I'm a lawyer, but I've specialized in physical security and locks for my entire career. We also run a lab at the University of Pittsburgh School of Engineering for senior engineering students to work on some of our patents and also some designs for security locking systems. So one of the problems that we've run into in the industry, the schools are not teaching anything practical. All of the engineering schools across the country, and actually also in Europe, they're teaching theoretical. The problem is when these kids come to work for lock manufacturers or government agencies, they have no practical experience by and large, and they also don't have any imagination and can't think outside of the box. So this is a real problem in our industry, as you'll see. So the examples that I'm going to present on video, I hope you'll find interesting. They really denote problems that we found and constantly find in lock design. Unless your agency or organization has real expertise in lock design and vulnerabilities and bypass tools, you probably won't know if there's vulnerabilities that can cause you a problem. So basically, InfraGard attendees, the real questions you have to ask is, what's your technical expertise? Do you have a thorough understanding of system bypass techniques and tools? Also, locks and audit trails that can be defeated, which can be a real legal and security problem. And everybody uses locks, but they may not know their vulnerabilities. So obviously, there are primary vulnerabilities in all kinds of locks, whether it's mechanical, electromechanical, electronic, or removable core systems. So what is insecurity engineering, which is the term that I coined many, many years ago and the industry has adopted? The problem, insecurity engineering by lock manufacturers. Locks, physical security, and access control systems are often not secure, even though they meet all the standards. Insecurity engineering, highlights the need to forecast, discover, and prevent insecure designs from reaching the end user. Why is it important? Locks and access control systems protect infrastructure, facilities, and people. High security locks may appear to be secure, but in our experience, they may be subject to compromise, often within seconds. Standards do not guarantee security, and how to assess the security of locks can be a very complicated problem. There's two books that I would recommend. One is Security Engineering by the late Ross Anderson at Cambridge University, where I've lectured for over 20 years, and my book, Tobias on Locks and Insecurity Engineering. There are complex issues involved in lock design, engineering, legal, technical, and security issues that both of these books cover. Okay, so insecurity engineering, why the term? Locks that have design flaws or vulnerabilities, and these can be embedded and not known for many, many years, as I'll show you in one of the videos involving the top high security lock in America. Engineers often do not understand different methods of compromise. Engineers, unfortunately, are taught how to make things work, but generally not how to compromise or defeat them. And this is a major, major. As I said, at the University of Pittsburgh, we have senior engineering students who really, uh, with 4 years of school, have no clue on a lot of security issues. Why can locks be compromised often within seconds? This is what we call insecurity engineering. Why I wrote the book? Basically, to identify and minimize design vulnerabilities in locks and security hardware. We find these problems everywhere, both in the United States and Europe. Design defects can be critical for liability and security. Also, to provide a roadmap to analyze locks and access control systems for security vulnerabilities and how they can be exploited. I'm working on a new book this year, which is the backstory of insecurity engineering, that will go through the mental and physical processes that my partner and I go through to identify and exploit vulnerabilities in locks that are supposedly secure and cannot be compromised. So why you need to understand the concept. You need to understand how different locks could have been compromised, or to analyze systems that you're looking at buying or purchasing or installing. Provide ideas about target locks and a way to assess whether they are secure against attack. Ideas on reverse engineering security for covert entry teams and facility protection. We are mainly interested in covert or surreptitious entry in the work we do. And what are the different tools and techniques available to defeat locks? So we have developed a number of rules that are listed in the book. I've only selected about 25 of them that are relevant out of 180 in lock design. The first and most important, the key never unlocks the lock. What it does is it actuates the mechanism that allows the lock to be unlocked. Most design engineers, honestly, they don't think about this issue. All locks are mechanical, whether they're electronic or not, because every lock, something has to move to make it work. We attack what moves. Basically, as I'll note later, the hardware software interface. That's what we go after. And that's usually what's vulnerable. Just because it is patented does not mean it's secure. The patent office does not test for security. It just tests for the legal criteria to issue a patent. Do not rely on standards. They're guidelines, but a lot of the standards do not encompass the way we defeat locks. Every locking system can ultimately be compromised. Remember our 3T2R rule, which is how much time, tools, and training does it take to compromise the system. So important primary rules. All security is about liability. Always believe you can defeat a lock. Look for simple solutions to solve what appears to be complex problems. We've worked some very complicated cases involving lock design and compromise, and ultimately it turned out to be very simple to defeat. Look for exploiting a design combination of designs in simple or hybrid attacks. We call hybrid attacks what we use two or more different forms of attack to compromise or neutralize a system. And things are rarely what they appear to be. R&D costs money, and many companies take shortcuts. Any openings in locks creates vulnerability. If it's a 10,000th of an inch opening in any area of the lock, it can allow us to compromise the mechanism. Look for the path of least resistance to unlock the lock or defeat the system. Remember that you don't know what you don't know about a lock. And if a manufacturer tells you it's impossible to defeat this system or almost impossible, don't believe it. Because in our experience with working with many manufacturers in the US, Europe, and the Middle East, they don't know. Use your imagination and consider hybrid attacks. More rules. This is really important. Electronics don't open doors, mechanisms do. Every lock has something that has to move. Credentials and encryption to us means nothing because we go after the software hardware interface. E-cylinder defeats bypass the credentials at the hardware software interface, as we'll show you in one of the videos. Locks are designed to be attacked. All exploits replicate what the key does. The easiest way to open a lock is with a key, or more importantly, a simulated key. Programming access and audit capabilities can provide security vulnerabilities. One of the examples is the ePlex that we'll show a couple different videos. A very popular lock that's used at military bases, government, commercial establishment. We figured out 6 different ways to compromise this lock. Clever does not mean secure. Even though a design is clever, it doesn't mean it's secure. And you cannot get around the laws of physics. You must examine both critical and non-critical components for a component failure analysis. Even a component that may not appear to be relevant can be exceedingly important in the overall compromise of a lock. So the video examples that I'm going to go through, Medico code setting keys that we developed 15 years ago. We developed a set of 4 keys that allowed us to pick or bump any non-master keyed Medico cylinder virtually anywhere in the world. Now, I have to point out on all of these case examples, as a disclaimer, all of these issues by the manufacturers have been fixed, especially in the case of Medico, when they came out with their new lock in 2023, the M4. Everything has been remedies that we found, but that also doesn't mean that there's not new methods of attack. Electronic clocks defeat with shock, vibration, magnetics, and laws of physics. I'll run some videos for bumping, the use of magnetics, shock, and vibration. ILOC systems out of Finland, which you're probably not familiar with, but they've actually come to North America and are making a real push to sell their products. These are energy harvesting electronic cylinders, no batteries. They use the key to generate the energy to open the lock. Unfortunately, years ago, and this was patented, won all kinds of design excellence awards, presidential award in Finland. It didn't mean anything. We could open their locks in seconds. Now, again, they fixed them. They're very good now, but it took them a long time to get there. The Dormakaba ePlex, we'll show you 2 videos. the EVA MCS out of Austria. These are very high security mechanical locks using a very sophisticated magnetic system. It's called the magnetic code system. They could not be defeated. Even the KGB that I interviewed tried with laser beams. They couldn't do it. I'll show you the video of what we did. The LockTech Rayonics is a cylinder that will demonstrate and also bumping and high security padlock. So let's go to the videos. So this is a worm gear. Some of you may be familiar with this. These are motor driven gears. You can see in the left hand side of the screen that when you enter the correct credential, it will move that gear and move a locking element to an unlocked or a locked position. So this is a very popular design in Europe, not so much in America, where you present a NFC or RFID credential to the face of the lock. It would decode it. If the credential is correct, it'll move the worm gear to an unlocked position. There are many, many manufacturers of this. A lot of them use worm gears. So we figured out Newton's first law of motion, the physicist from almost 400 years ago. We used his first law of motion to open this lock rapidly. So my partner, Tobias Blues-Manis, will demonstrate what we did. And basically, we spun the cylinder. Now, all of the manufacturers thought they properly tested this by using a drill motor and spinning it at different speeds. That wasn't the problem.
Well, I don't know how many.
I think it's about 11. I think maybe 11.
So we just attached the
But you're going to
mechanical
slowly
element.
see that piece move forward, which is obviously the critical issue here.
Watch my hands.
Yeah.
You actually can see from the top camera that the two prongs already extended.
Yep.
It's extended as much as we can. So actually, right there.
And it's open. And so this is precisely the problem. We view this as a serious issue, for a security issue. And now if we reverse this, we'll go backwards.
Okay, so let me just comment. You can do that attack all at once, or you can do it in steps. So you can walk up to a lock and basically set it in advance. So let's talk about Medico high security locks. This is the top high security lock, or one of them in the United States, sold throughout the world. In 2000, announced they were bump proof. We received 4 US patents, and we wrote the book Open in 30 Seconds. And they, as I noted, they have revised their design to make this much more secure in 2023, using the M4 with another level of security. So for those of you that may not be familiar, this was a groundbreaking invention in 1968 by two guys in a garage in Virginia, Salem, Virginia. They figured out that they could take a pin tumbler lock and they could not only lift the pins, they could rotate them. So I did a diagram showing the different angle configurations on a Medico key. And the bottom, you can see all of these pin tumblers, the little channels here, they're all in perfect alignment which they have to be for this lock to open. So this was an exceedingly difficult lock to pick and bump open. So we developed what we call code setting keys. We basically took the 3 rotation angles, 6-pin tumbler depths that made 729 different codes or combination of angles. We combined those in 4 different keys. So basically, it allowed us to pick or bump all non-master keyed cylinders, basically anywhere in the world, because the code book that was required to cut these keys was standard. So in 2007, those are what the keys look like. They all have different bitting surfaces. These are the keys. So in 2009, Wired magazine did a feature article about what we did at their Wired headquarters in New York. This is a very demonstrative video, so I will run it.
Hi, I'm Charles Graber with Wired Magazine. We're in the Wired offices here in the Condé Nast Building in New York. It's 12th of February 2009, and I've got a box of Medico cylinders that we're going to be testing. We've got Tobias Buzmanis and Marc Tobias here who are going to be opening these cylinders. We're going to take them one by one without showing them, put them into the vise. They're going to use their tools and technology to try and crack them open in less than 10 minutes each. So let's get started. Go.
I'm using code setting keys with 6 pins. It's not helping. The device is slipping a little bit over there, but let's see.
So we had to use a paper clip. That's what's inserted in the keyway on some of these to bypass their slider mechanism, which was additional security and key control.
1 or 2 more pins. Was 1 open?
This is a high security lock.
Go.
Well, this is a 5-pin. Medical M3. Open.
Okay.
Open.
Those are our code setting keys.
4. 5. Open. Open. Open.
Okay, so that's 6 locks. We went through. The fastest time was 1:55. That was lock 5. The slowest time for picking was 8 minutes 13 seconds. All of them were below the 10-minute threshold. That's the absolute minimum for the more stringent threshold for high security locks. That's the UL standard. The BMHA
Is the most stringent.
is more stringent.
And that's up to 15 minutes.
Correct. Right. And so essentially all these locks failed, at least according to the standards set by the industry. All these locks fail to be high security.
Is the pepper click okay like that?
Yeah, not really, but it's open. We done? Okay, so basically, and there's the book that we wrote in 2007. That's a very detailed analysis of the steps that we went through to figure out how to do this. Basically, we generated keys out of shim stock that bypassed every restricted keyway. That's the flat keys that you saw, and they were specially cut. So this is the next example. This is iLock out of Finland. This was a very clever um, industry leader in Finland. This is an energy harvesting lock, so it's totally electronic, but it's also mechanical. And when the key is inserted, there's a credential in the key. When you insert the key into the lock, it generates a current, charges a capacitor, evaluates the key. If it's the correct code, then it moves a pin right there, and the lock will open. The problem is that we figured out several different ways to compromise this lock. It was designed by software engineers. They weren't lock designers. Now, to be fair, the company has made a lot of strides, and now they produce a really good energy harvesting electromechanical cylinder. But basically, we figured out how to set the lock once, and I'll show you and do some modification of keys, either the front of the lock or a valid key that would allow anybody to open that lock. So basically, the top picture is a valid key. All the keys are the same mechanically. So what we did was we trimmed 1/32 of an inch off the tip of the key in the red ring. This would cause a failure of the reset mechanism in the lock, or we went up with a handheld Dremel tool, battery operated, to the front of the lock, trimmed the same thing on the front piece that was accessible, and then we could just walk up with any key, use a screwdriver, and open the lock. So as I said, it was very clever. And then we figured out there's a video online that shows how we also defeated their timing window to open the lock. This was an electronic cylinder. Um, in the upper right-hand corner of the printed circuit board is the terminal that we needed to activate the little motor drive. So we went through with an insulated lead through their plastic, and we caused, for direct motor access, caused the lock to open. This is a lock tech. This shows what happened with shock and
This
vibration.
involves the Rayonics Lock Touch e-cylinder. This is basically a knockoff of what's produced by Videx, and to a limited extent also by Medico. We looked at this, we were sent a couple samples. One of them wasn't programmed, and that's the one we analyzed and attacked. They have the same problem as other compatible cylinders, and that is that the locking system is based on an internal motor and rotor that turns 90 degrees. The problem is that the rotor has too much, the actual rotor element has too much mass, and so we can vibrate it to a 90-degree position, which will allow us to unlock the cylinder using the key. And it's pretty simple. The problem is, from our standpoint, this denotes a lack of understanding by the engineers at Rayonics that we found in other manufacturers as well, as to the use of shock and vibration in defeating these cylinders. Toby, you can make comments, and then let's just wrap this open.
Well,
It's
let's
pretty
open it
straightforward.
first,
Yeah.
and then we can add some comments. So the key doesn't have anything. It's totally,
Yeah, there's nothing active in
yeah,
the key, so it's purely a mechanical key right
yeah.
now. Yeah.
So all the electronics are out, but that's what we need. We just need the basic key
Let me see how I can do this without blocking but just putting.
And it's open. And that is a real problem, obviously. This involves.
Okay, so this was a lock that was sent to me for urgent analysis. This is not our normal way of doing videos. This was in my den, and I had to handhold the lock because my client, or our client, needed an immediate response. This was a European locks design.
Okay, this is an Iseo lock. This is going to be a very rudimentary video. We just received this for analysis. This is an electronic cylinder. You can see that the key works. Let's see here. Key works on the non-electronic side. So let's do it this way. I removed the battery so you can see that the lock will not open. So now if I can do this, here, let's do it this way. Hold on one second. Yep, it's open. Yep. Okay.
So that may seem simple. 15-year-old kids are bumping open locks. We introduced it to America in 2007 at DEF CON with an 11-year-old girl opening locks. It is still a problem in the industry because you can't get around the laws of physics. So this is 2 electronic cylinders that, again, have been totally fixed, the problems, but these were earlier cylinders. And I'll go through and show. Okay, so basically what we figured out is we simulated the mechanical key, and we could go through with a shim wire about 10,000ths inch, and we could go through a feed-through hole in the printed circuit board and drive the element to a locked or unlocked position, which is what the rotor control would do with a worm gear. So that's it's locked. Now it's unlocked. And so here's what we did, and you'll see we produced a key for the lock. The mechanical side we replicated, and then we put a wire exactly spaced to go through the feed-through hole on the printed circuit board to access the rotor. You can see the wire coming out. So when you put the key into the lock, we pull that out, and the lock is open. That's the normal key. So there's no electronics in this lock. Pull the wire, the lock is open. Very simple. Here's the other one we did with shock and vibration. And we also did that with a different kind of key for a different company that also used the same theory. This was a really cute defeat. This is a electromechanical lock that's used in a lot of apartment houses, government facilities. It's a deadbolt cylinder with an RFID card, and it has a data port you can see at the bottom of the screen for programming. Well, the manufacturer never thought that we could run a shim wire.
Inside there is a locking bar that blocks the plug. We're gonna be using a small wire to push that locking bar away so we can turn the plug. We're gonna do that by inserting a very small wire through the communication port that is on the bottom of the lock. We're gonna now use the wire to unlock the deadbolt, and we can also lock it back. This is the inside of the soft lock deadbolt. This is the locking bar that blocks the plug. There is a small motor that moves that pin up and down. We're moving that bar using that small wire through the communication port. Just reaching to that bar, moving up to clear the fence so we can turn the plug. Inside
The lock is open. Okay, so this was one of the best high security deadbolts was and is in the States. We came across this by accident. We were looking at another manufacturer deadbolt, and we figured out how to take a $2 screwdriver, go through the keyway, which is open, break the two 83 thousandths inch screws that retain the back of the plug, and use a screwdriver to open it.
Okay, for the medical deadbolt, we're going to use first this tool right here. Notice the lower portion, because we're going to introduce this tool like this, and then we're going to put the tool straight, break the back cover, remove the tool, and then using this one from the lower part of the cylinder, then you're gonna raise it all the way. You can see the bolt. Raise it, push it in, and turn.
That's it. And this is the back of the cylinder. You can see the two screws that were sheared. They did an interim fix, and it was partially successful. Now this was a long time ago. This problem has been fixed, but again, it demonstrates nobody thought about what really holds the lock together and how to defeat it. So this was a colleague in Germany who developed what's called the magnetic ring. You can see it there. 4 magnets encased in an aluminum structure to attack cylinders with magnetic elements. No electronics in the key. So that key doesn't work. That's the magnetic ring. Again, no electronics in the key. And the lock is open or unlocked. Now, again, this problem has been fixed, but the industry suffered from this years ago because they didn't understand how magnetics and strong magnetic fields could be applied. This is a really famous case that I was involved in, involving axial pin tumbler locks, which can still be a problem. That were in the kryptonite bike lock. The company Schlage actually had to recall 350,000 bike locks because we figured out how to impression these with a ballpoint pen. Okay, so this is the Kaba 5800. You may recognize it. This is the Kaba E5800 E-Plex series. This is mechanically the same platform as the 5000. We're going to go through and show some of the same attacks that the 5000 is vulnerable to. First, we'll enable the remote open function and show how to bypass the system by inserting actually a metal pick and shorting out the control pin.
Let's do it also then on this lock. Right there.
And the lock is open. This is another version where we use shock and vibration.
This is the E-Plex 5800 demonstrating the same vulnerability with regard to applying shock to lift or bounce the locking plunger assembly in order to open the mechanism. Toby?
And that's what's happening in the lock. This is the Simplex 1000. I'm sure many of you are familiar with this.
Well, normal use lock is a clutch lock. We have to put the right combination. Factories 2 and 4 at the same time. 3, we can open the lock. Once, if we make a mistake, every time that we depress the lever, it resets, so we can enter the right combination again. Okay, so on this lock, as Mark said, is easily bypassed using a magnet. I have the magnet just wrapped in a bag. I'm just gonna depress the lever, the lock is open.
Okay, this is the, I think, the last video because we're going to run out of time. This is the EVA magnetic code system out of Austria. This was developed about 35 years ago in consort with 2 universities. There's 4 rare earth magnets that show up on both sides of the key that can be encoded. This is a very high security lock. So this is what the rotors look like. It's much like a safe lock. And this is what happens inside the lock. You can see right now that all of these rotors are in alignment with the correct key. There, they are not in line, so this lock cannot be opened. So we figured out how to create a second key because of an engineering problem that they never considered. And we'll just go through this. This tool you should be aware of. We're going to end the videos. This is an electronic decoder for locks. You all can see the video later. This is an electronic decoder also. And this would be my recommendation. I'll throw it open to questions. Corey?
Okay, we have a lot of questions. We'll see how many we get through. Okay.
Yeah.
How much time?
Yeah. The question is, why haven't they locked us up?
How much time do you spend on average when examining a new lock to determine the methods you'll use to bypass the lock using non-destructive techniques?
It depends. It can be 5 minutes and it can be 100 hours. It really depends on what we're familiar with, our experience, similar mechanisms. We never know, but we've seen an awful lot of locks. So usually we're pretty good at what we do, but it can take short time, long time. It just depends.
Does wire EDM precision cutting change anything in the security of mechanical lock mechanisms?
Well, it does, but in picking tools especially. I interviewed the chief KGB agent from Riga Latvia, and he said nothing has really changed except the machining, the metal, but it's all the same theory. If you read the book, I went back 200 years, and the new book as well. It's all the same theory because it's all the same mechanics.
Going back to the university issue that you pointed out earlier on, is it the fault of the student that they do not understand the material, or the institution to help the student learn the material by providing the appropriate material?
See, institution. I've talked to our deans a lot. All the schools are concentrating on theory. That's great, but honestly, unless they've had internships, they don't know how to apply it. And there's a lack of imagination. So that is the problem.
How involved are major lock manufacturers in addressing the kinds of insecurity engineering issues your team identifies?
They try to be involved. Look, nobody wants to produce a lock that's not secure, as I'm pointing out in the new book that I'm writing. The problem is they don't know a lot about the way we attack locks. They don't know a lot of the tools that are available. And again, it's a lack of imagination on the design engineers. They get focused on what they develop, and honestly, we just keep showing them how they can be compromised that they never thought of.
Many of us assume that certified locks are inherently secure. Can you explain why certification doesn't always guarantee real-world security?
Well, first of all, it's really not certification. It's the UL 437, which is a commercial security standard. It's not really a high security standard, and it's integrated with what's called BHMA 156.30, which is the commercial high security standard. The problem is we're opening locks in ways that are not specifically defined in the standards. The standards are a great guideline. I just met with the head of BHMA over Christmas, and the standards cannot identify every way to open locks. So they really, like I said, they're guidelines. They don't guarantee the security of anything.
When do you expect MasterLock to implement a fix from people using comb picks to quickly bypass the tumblers by overextending them?
Read the book. Comb picks go back a long time. A lot of manufacturers do not understand what are called balanced drivers. So the pin stack has to be equal with top pins and lower pins. I really went into this in detail, and we developed, and it's going to be in the new book, some very sophisticated ways of using comb picking with the injection of ball bearings into the upper chamber. I think I covered it in the last book also. It's a real problem.
Side note, you all will receive a link to Marc's book in the follow-up email you'll get with the CPU certificate. It appears that most of the testing is done with the locks outside of a door. Do they confirm this testing again with the lock installed properly in a door or housing for all tests?
Not for all tests, but we go through. We use a vise. We replicate. There can be some differences, especially in bumping, because of damping of energy. But essentially, if we can open it outside the lock, we don't come up with any videos or information for our clients that we can't confirm inside a door lock or inside mounted in a door. So we're very careful about that because there are all kinds of legal implications. But whatever we do with a cylinder, we can do inside of a door.
How vulnerable are non-keyed locks, such as those controlled by card readers or credentials, to activate?
Well, first of all, we're not software experts. That it's not our deal. We do have some software experts that we use. Um, it's a whole different set of vulnerabilities. And frankly, when I've lectured about digital locks, my rule is if it's a digital lock, don't trust it because there's lots of back doors. You can use EMP, RF. There's lots of different attacks. And, and every day the hackers are developing new attacks. So we like mechanical locks. I'll tell you why. Because we know what's inside of them and we know all their secrets. If you understand the lock, you understand how it can be opened.
In your research, what are the most common design decisions that unintentionally create vulnerabilities in modern locks?
That's a hard question to answer because design vulnerabilities can be anything. Simple components, the way they're put together. If you read our book on Medico, and we love their company, we're not picking on them, it's just their leader in the industry. They made some design mistakes. They got great engineers. All the companies we work for, they got great engineers, but they don't know a lot of things. And as I said earlier, they don't know the tools and they don't know a lot of techniques. It's a failure of imagination. If you read Dr. Roger Johnson's book, he was the head of vulnerability assessment at Los Alamos. He goes through this also. It's just a real problem.
One more question. What trends or technologies are emerging that you believe will change how we think about physical access control over the next 5 years?
Well, it's all the integration of electronics and sophisticated encrypted credentials. But again, everything in a lock, something has to move, and that's what we attack. So what you really need to look at, like strong magnetic fields, EMP, RF, shock and vibration. Um, there's a lot of testing that we go through depending on what the lock is, but it's all going to be integration of electronics. The manufacturers are all moving to this, but honestly, I'd rather have a good, well-designed mechanical lock to protect my assets.
Mark, thank you so much for this fascinating session. It's not often that we get to have an inside look at how locks are designed and how design decisions themselves can create vulnerabilities. This has been a truly eye-opening discussion, and I know our members and guests will take away valuable insights about applying real-world thinking to physical security. Quick reminder to all attendees, you'll receive a follow-up email later this week with your CPE certificate and a link to a few resources that Mark is going to provide. Thank you all for joining us today, and please keep an eye on the InfraGard National Newsletter for upcoming webinars and training opportunities. Have a great day, and Mark, thank you again to you and your team at Security Laboratories for your continued support of our mission.
Yep.
Have a
Thanks
great day.
everybody for attending.